we often use to describe the gas exchange units of the lungs. So when we were talking about the lower airways, what were the two types of airways we talked about? Like we kind of broke it up into these two areas.
Respiratory.
Yeah, so there was the conducting zone. And what's part of the conducting zone? The trachea, main stem bronchi.
Generation of 1 through 19.
Okay, so we go from the main stem bronchi to the lobar bronchi to the segmental bronchi to the subsegmental bronchi to the bronchioles to the terminal bronchioles. All those structures are part of the conducting zone. So when we talk about the units of gas exchange or the areas of gas exchange, we're specifically talking about the respiratory zone. So what makes up the respiratory zone? Respiratory bronchioles?
Alveolar ducts and sacs.
Alveolar ducts and alveolar sacs. So what do you, of this picture, on this picture, these right here are going to represent our respiratory bronchioles. It's kind of that straight line area. This right here is the alveolar duct, which then makes each of these the alveolar sacs. That's a chair. So lots of things kind of communicate and happen in these areas that it's important to label. So we touched on this briefly. I really hope this red pen or marker works. We touched on this briefly when we were talking about the structures that make up the lower airway. So we have these areas that provide us with like tertiary ventilation, right? It's another way that we can get gas from, say, the respiratory bronchioles to alveoli. And we call those, this area here, would be canals of Lambert. So just like the Suez Canal helps ships get from one body of water to another across a land mass, our canals of Lambert help gas or allow gas to move from a respiratory bronchiole to an adjacent alveolar sac. That is not to be confused with this structure that I just made here. So when there's a gap, like a hole in the wall of between alveoli, what is that called?
Pores of Kohn.
Pore of Kohn, yeah.
Pore.
So this space right here is a pore of Kohn. And what purpose do they serve? Any guesses?
Permit gas to move between adjacent alveoli.
Yeah, so it allows gas to move from one alveoli to the next one, the one that it shares that pore of Kohn with. So if this alveolus gets really filled with air, it doesn't want to rupture, that would be really bad. So rather than rupturing, a pore of Kohn will allow gas to move to a less filled alveolus. All right. Next, we'll talk about the cells that make up the walls of the alveoli. So, what sorts of cells did you guys read about?
Type 1, 2, and 3.
Type 1, 2, and 3. So type 1 is the most common cell that lines the alveoli. All right. Another name for a type 1 cell is a squamous pneumocyte. So these type 1 cells make up like 95% of alveolar walls. Right? They're just these single layer, short, wide cells. And they allow for gas to move up through that alveolar wall. Type 1 cells cannot regenerate themselves. So if a type 1 cell dies, it can't replace itself all on its own. So what has to happen is a type 2 cell has to populate. So a type 2 cell can also be called a granular pneumocyte. It makes up the other 5% or so of the alveolar wall. I can probably label these with an E. So, cool things about type 2 alveolar cells. They are able to transition from a type 2 cell to a type 1 cell. So if this friend dies, this type 2 cell will become a type 1, but not before it replicates itself. Other super cool thing and really important thing that a type 2 alveolar cell does. They are responsible for creating and excreting surfactant. I'll write that here. So what is it that pulmonary surfactant does? Well, it reduces surface tension on the wall of the alveolus. So surface tension is the tendency of liquid molecules to want to come together and stay together. So when you have a raindrop that hits your windshield and it's running down your windshield, it's always going to find its way to other raindrops, right? To create bigger raindrops. That's because of surface tension. So we know that outside of our alveoli is liquid, right? It's the interstitial fluid, which we'll talk about too. But there is liquid outside of the alveoli. And so those liquid molecules want to come together, and they want to come together so tightly that they want to collapse the alveoli. So those type 2 cells secrete surfactant, which helps to reduce the surface tension on the outside, the wall of the alveolus, so that those water molecules can't pull it together and ultimately make it collapse. Anything I need to repeat there? Make sense? We'll talk a lot more about surface tension when we start getting into some concepts like compliance. All right? Then lastly, we have another type of alveolar cell. And I'm going to draw this guy. Oh, golly jeepers, that is not a marker. How about purple? Oh yeah, there we go. So that is a type 3 alveolar cell. This type 3 alveolar cell can also be called a pulmonary macrophage. So type 3 alveolar cells are responsible for moving around throughout the alveoli, kind of free floating, looking for trouble. Right? Type 3 alveolar cells are looking for some sort of debris, whether that's a tiny little virus or a tiny little bacteria or dust, some sort of thing that's not supposed to be in the alveoli, and it will eat it. Get rid of it. All right. These are pretty big cells. They're a part of our immune response, so they're generated by the immune system, but they only then live in the alveoli, these pulmonary macrophages. And the other neat thing about them is that they're probably responsible for creating the pores of Kohn. So a pulmonary macrophage can be in one alveolus and sense that there's some sort of invader in an adjacent alveolus and just bust through the wall and say, I'm here, and eat it, because they're really hungry all the time. Always looking for trouble. So that's we're not entirely certain that that's why we have pores of Kohn, but it's the leading suspicion, the leading theory that makes the most sense. And then all this space kind of outside of these alveoli is an area that's called the interstitial space. Sorry if you can't see that. Can you see that okay over there? Okay. It's an area called the interstitial space. It's filled with a kind of gel-like fluid, and it's comprised of these two areas that we call the loose space and the tight space. I'm changing marker colors, okay? Come with me. So these are going to be our interstitial colors now. So the tight space of the interstitium is located, change the color, sorry, is located here. It is the area in between the wall of an alveolus and the wall of the pulmonary capillary. I have been butterfingers all day today. I have not been able to hold on to anything. So this area here, this straight line, is the pulmonary capillary. So we've got all these cells here making up the wall of our alveoli. Imagine it's on the other side too. So tight space is right between the wall of the alveolus and the wall of the pulmonary capillary, which then means that all this other space, everything else, is the loose space. So what happens across the tight space is that gas is able to diffuse out of the alveolus and into the pulmonary capillary because it's tight. There's not a bunch of fluid in between those structures. In the loose space, all the other things live. So things like lymph vessels live there. Our lymph nodes are located in the loose space. We've got some canals of Lambert that can live in those areas. And some blood vessels can be there too, bigger blood vessels. What would you call this? It's a gap between two alveoli. core of cone. So that's represented there, that's a core of cone. Questions about what's happening structurally? We're all good here? Okay. So now we're going to dip our toes into the pool of possibilities when it comes to diffusion and pressure gradients. Okay? So what are the two gases that are associated with respiratory care? Two main gases.
Oxygen.
Oxygen, that's a big one.
Carbon dioxide.
Carbon dioxide. Okay? Those are the two gases, the two primary gases that we're diffusing across what is called the AC membrane, or the alveolar capillary membrane. Which is another term that we use to describe the tight space of the interstitium.
Did you say it was the A?
AC,
Yeah.
alveolar capillary membrane,
Okay.
which is another term that we'll use to describe the tight space of the interstitium. So when someone inhales, what are they taking in? What gas? Oxygen. So right here, we're gonna say, and I'm gonna draw it over here just because I don't have any cells over here, but just know it's gonna enter both alveoli. So we have O2 that comes in the body when we inhale. And the partial pressure, approximately, of this gas is 104 millimeters of mercury. At our tissues, when our body uses that oxygen, what's our body create? It's a byproduct of cellular metabolism. Carbon dioxide. So here in our pulmonary capillary, blood's whooshing by, right? Always moving, always moving. And it's moving so that it can pick up O2, but it can also then drop off CO2. So we have CO2 in the pulmonary capillary, making its way to the alveolus. And the partial pressure of the CO2 in that pulmonary capillary is about 45 millimeters of mercury. And those numbers are important because it's what creates the pressure gradient that causes diffusion, that causes gas to move. Gases want to move from an area of high concentration to an area of low concentration. So in this blood, in the pulmonary capillary, the partial pressure of the CO2 is 45 millimeters of mercury, but there's also some leftover oxygen. So in this vessel, the partial pressure of oxygen is about 100 millimeters of mercury. And that's the reason why it's going to move from the alveolus, where it's higher, into the blood in the pulmonary capillary, where it's lower. Now, when we exhale, we also don't exhale all of the CO2 that's hanging out in our alveoli. So there's some CO2 that's here as well. and that has a partial pressure of about 40 millimeters of mercury. Which is again the reason why, as this blood is whooshing by, that CO2 is going to move from the area of high concentration to the area of low concentration. What can I repeat?
So the CO2 is moving from the capillary into the
Alveoli.
alveoli.
Yes.
And then the oxygen is going from the alveoli to the capillary
That's correct.
to match and lower each of them.
Yeah, to balance out that pressure gradient.
Okay.
And these gases will continue to move if blood just stayed put, which it doesn't. Ideally, otherwise you're, well, dead. But as long as that blood flow is moving, then those gases will never actually reach equilibrium. But if it did stop, if that blood flow did stop, then those gases will continue to diffuse back and forth across that AC membrane until they reach equilibrium. That's to say that there's the same partial pressure of gas here as there is gas in the alveolus. But we never reach that point because our blood just keeps moving. Later on we'll talk about reasons why it doesn't, but no reason to get there now. What else? Anything else that I can repeat? So you're with me? This all makes sense? Okay. Things that I want you to bear in mind. I'm less concerned about you memorizing these numbers as much as I am you understanding the concept. Understand that there's going to be, when we inhale, there's more oxygen in the alveoli and less in the pulmonary capillaries. And that's why it diffuses that way. Likewise, after we inhale, there's less CO2 in our alveoli and more in our pulmonary capillaries, and that's why it diffuses the opposite way. Okay? That's gas exchange. That's what we're getting through for gas exchange. So then we'll move to pulmonary vascular system. So, tell me what you know about arteries.
There's 3 layers to an artery.
There are 3 layers to an artery. Where do arteries take blood? Away from the heart. So this is a big sticking point for me. So I know that there's always anatomy classes, I'm not saying here, but there's always an anatomy teacher somewhere that says that arteries carry oxygenated blood. Yeah, they don't always. There's a really particular situation that matters a lot to us where they're not carrying oxygenated blood. So, always remember that arteries are carrying blood away from the heart. That same anatomy teacher will always say, veins carry deoxygenated blood. Which is also not entirely true, because there's 4 really important veins to an RT that carry oxygenated blood. So, veins always carry blood where? To the heart. So after today, if any of you ever look at me and say that an artery always carries oxygenated blood, I'm gonna cry. I'm gonna cry right in front of you. That's not true, I won't, but I'll be really unhappy. So, when we are talking about these vessels, I'm going to use colors that we're all familiar with, but just bear in mind that that classic like red and blue kind of vein to artery scenario, just toss it right out the window, it no longer matters, all right? So there are 2 pulmonary arteries, and they originate in this, this area here. What's that called? What's that chamber called?
The right atrium.
Love it. That's not though. It's the right ventricle.
Ventricle.
So this is the right atrium. So left atrium, left ventricle. So these pulmonary arteries originate from the right ventricle. And they kind of eventually bifurcate into the right and left pulmonary artery. Please don't take my bifurcation to heart. Again, this is high school C artwork. There are 4 pulmonary veins, 2 that come from each lung. And they dump into the left atrium. It looks like a lot, sorry. So which of these is carrying deoxygenated blood? The arteries, so these red ones. Pulmonary arteries carry deoxygenated blood. Those are those big vessels. We can also, they'll be called great vessels on the anatomage table. So those are when they're at their biggest. But after the pulmonary arteries, once they make their way into the lungs via what structure? What structure do the pulmonary arteries, pulmonary veins, and mainstem bronchi enter the lungs? What?
The hilum.
The hilum. So as they make their way into the lungs through the hilum, just like our lower airways get smaller and smaller and smaller, the same thing happens to our blood vessels. So we go from these pulmonary arteries and then to just like kind of regular arteries. Then we get to arterioles, which are slightly smaller. And then those arterioles will get even smaller and become pulmonary capillaries. Pulmonary capillaries are just like up here, and they're single-walled vessels, or single-celled vessels, so one cell makes up the wall, just like the alveolus. It's gotta be really thin for gas exchange. Those pulmonary capillaries, after they pass by the alveoli, will get a little bit thicker and become venules. And then the transition from venules to back to veins and pulmonary veins gets a little bit dicey, but at that point you're kind of splitting hairs. So the biggest thing that makes these things, the differences, the transitions, is really the walls of the vessel. So Kennedy said that that arteries, the pulmonary artery certainly is included in this, are made up of 3 layers. So one of those layers is a smooth muscle layer. And that smooth muscle layer helps to create pressure inside of the vessel. And that pressure inside the vessel really is what generates blood pressure in the systemic vascular system, and it generates pulmonary blood pressure, like a pulmonary pressure, pulmonary vascular pressure, inside of our pulmonary circulation. Okay, so that muscle layer is going to create pressure needed for blood to move. Okay, and so these vessels are also called resistance vessels because they're creating pressure. We can compare that then to our veins, and our pulmonary veins are certainly a part of this. There's also 3 layers, but there's not much in the way of muscle. There's not much of a muscle layer in our veins. They're a lot stretchier. And so these vessels, rather than being high resistance vessels, are called high capacitance vessels. They can take on a large capacity or a larger capacity of blood. Arteries are more like that awful no-stretch denim, whereas our veins are like the real nice stretchy jeans. So your stretchy jeans, more forgiving, you can put more in them, versus your no-stretch jeans, can't put as much in them. Create more pressure when you try to button them. I went through that this morning. I didn't know I was grabbing no-stretch jeans until I was already like, oh no, they won't button. So the intention of that, the importance of that is really vascular tone, okay? So vascular tone is really just the concept and the functionality of that smooth muscle layer. So that smooth muscle layer is able to dilate or constrict to create, it dilates and it creates a lower pressure. If it constricts, it creates a higher pressure. So you either allow blood to move more forcefully or less forcefully. So vascular tone is just the functionality of that smooth muscle layer. So when the smooth muscle dilates the vessel, it makes it bigger, then there's less pressure. When that smooth muscle constricts, it makes the vessel smaller, so then there's more pressure in that vessel. So vascular constriction, arterial constriction, will increase blood pressure. Vascular dilation, when the vessel gets bigger, will decrease blood pressure. Arterial blood pressure.
What did you say again will increase it? Arterial.
Constriction. So the smaller the vessel, the more pressure, which means the higher the arterial blood pressure. All right, so some other things I want to make notes of. So one of your objectives asks, what is it that provides perfusion to the pulmonary system? And the main vessel that's responsible for perfusing, or rather taking nutrients, things like that, to the pulmonary system, to the lung parenchyma, are arterioles. So they take the nutrients. It does hold on to some oxygen, because our tissues won't just use all the oxygen that's in our deoxygenated blood. So it's able to take some of that perfusion, take that nutrition to the lung parenchyma. The other thing I want to talk about is a term called venous admixture. So, these vessels, right, these three vessels, there's, again, the division between an arteriole to a pulmonary capillary is really based on the cell wall and its location, right? If it's a single walled vessel and it's running right next to alveoli, then it's a pulmonary capillary. But these arterioles will eventually become single walled vessels that maybe don't run directly next to an alveoli, okay? Likewise, when that transition from pulmonary capillaries to venules happen, again, it gets a little dicey. It's really based on location, whether or not it's directly next to alveoli. A part of that then is that they're not always pressurized exactly like arterioles versus capillaries versus venules, okay? And what that means is that there's opportunity for blood to kind of hang out in one particular spot. There's always constant blood movement, okay? But much like, so I told you guys, I live at a lake. So there's always a time where like the top part of the water is like constantly moving, right? It's always in motion. But then like the water underneath, like in the bottom of the lake, can get a little stagnant and just hang out in the same spot for a little while. The same sort of thing can happen in our pulmonary vasculature, all right? So there's times where like we're sleeping, or we're not moving around as much, or when we're sick, where blood can kind of hang out in the pulmonary capillary despite other blood like whooshing around next to it. And so that blood that kind of hangs out for a little while will have more CO2 in it versus oxygen. And then it all mixes together, CO2 and O2, to create venous admixture. So venous admixture is the mixing of oxygenated and deoxygenated blood, which just naturally happens. This is normal. Our bodies are made for this. It's made to handle this. And we call venous admixture a natural shunt. And in just a couple of short months, you guys will be so sick of hearing about shunts. I promise. But this is the easiest kind. That is also true. Questions about this? Okay, so the first thing that I want to say then as we move to the lymphatic system, before we go over to the anatomage table and take a look at some things, is again, one of your objectives asks, what is the lymph system, like how does it drain? So it drains directly into the thoracic duct, which then dumps into the left brachial vein, which then dumps into the superior vena cava. So really what this means is that the lymphatic system drains into our veins. Lymph fluid inherently makes up a portion of the plasma in our blood. So what does the lymphatic system do? What purpose does it serve?
Immunity.
Okay, it's a part of our immune system, or a part of our immune response. Yep, it removes things, excess fluid, protein molecules, carbohydrates, all sorts of things that can get kind of stuck in the interstitium, the loose space of the interstitium. And then our blood and various other places too. But what we're talking about right now is really here in that loose space. So it picks up excess fluid, excess things that shouldn't be in the interstitium, and move it back into the vascular system, move it back into the veins. And when we start talking about the immune system and immune response, we'll discuss the lymph nodes more heavily, but really lymph nodes serve as immune hubs. Lots of immune cells live there, and that's kind of one of the big places where these cells will say, ooh, I see something I don't like, and it'll like basically raise the army in the lymph nodes. Want to go see it? We can go see it on the anatomy.